So in this video, we're going to develop the Runge-Kutta Method project template. I want to start by reviewing two things. First, I want to review the learning objectives that I wrote in this rough draft of the template. And then I want to review the Euler-Cromer template from last time. Let's scroll down and just take a look at what the learning objectives were. So learning objective 1, compare the steps of the Euler-Cromer method with those of the Runge-Kutta method. So this is going to require a description here. And then we'll have them copy and paste their previous Euler-Cromer method code here for comparison. And then learning objective 2, compare the results of the ECM and RK4. So we'll also have them run the code at this point, and then write a discussion comparing the results. Let's see, then we have them adjust the initial conditions in the RK4 code. So we'll have them copy and paste the Runge-Kutta code here, and then they'll just change the initial conditions. And then they'll discuss the differences between the scattering and the bound state. Okay, so I'd like to keep my language consistent, so I'm going to take some sections from the Euler-Cromer project and just copy and paste, so that way I use the same terminology, the same kind of, instruction flow and everything. Let's see, we don't need this stuff at the beginning because they'll have used Jupyter notebooks by this point. So let's scroll down here. Okay, so I want to have something about this. Let's see here. So the copy, so this will be similar to for the Runge-Kutta description. So let's see here. This is learning objective 1, and I left the learning objectives in, right? Yes, I did. Okay, learning objective 1, compare the steps of the Euler-Cromer method with those of the Runge-Kutta method. Okay. In the cell immediately below, paste the Euler-Cromer method code. I think that should be paste the final version of the Euler-Cromer method code that you used at the end of the Euler-Cromer method project. And over here we've got Euler-Cromer method project. That should be a sufficient enough callback, I think. There we go. So we'll so this is where they do this. So this is where the student copies and pastes their Euler-Cromer method code here. And then here I need to have the Runge-Kutta code. So then I'll hit paste here. The following code cell. Okay, so how do I distinguish this code cell from this code cell? I guess I can just put in another markdown there. I guess that makes more sense to just have, one step per markdown cell. So we'll go here, we'll say add a cell. Good, it's currently code. I want it marked down. Do paste. The following code cell contains the implementation of the Runge-Kutta method. Do I need to specify that it's fourth order? I kind of feel like I'm okay leaving out the fact that it's fourth order because that's commonly referred to as the Runge-Kutta method. Present it in, and then I need the video for that. I forgot to open my videos page. I do have the GlowScript code up, but I forgot to open my videos page. So we'll go search for Runge-Kutta. Okay, so let's have them use the second order one. I think I only had 3 videos in this series. So let's grab this link, copy link address, because this one had second order. Yeah, this was second order with an adaptive step size. Presented in, there we go. To solve for the motion of a ball under the influence of a spring force. Okay, yes, that should be fine. We'll update the instructions. So I need to change the instructions here. Change the initial conditions and force in this code to match those from your Euler-Cromer method code above. There we go. Now we've got a nice comparison between the two. So here I can put in the Runge-Kutta code. Control C to copy, Control V to paste. Okay. I am going to need to make a few changes to this. To help me with that, I'm going to review the changes I had to make over here. So I need to have from vPython import star instead of the GlowScript 2.7. There we go. Let's see, what else will I need? I've got, what are the kind of changes that I have to make? All right, I have to set up a canvas at the very beginning. Do I have to make any other changes up here? I have some comments. No, everything else is fine. Canvas, graph. Oh, I suppose I need to have them set the max time to be the same as well. Let's see here. Change the initial conditions. Force, maximum time, etc. Meaning there may be other things you need to change. You have to figure them out. But I don't think you will necessarily. Let's see here. So this is the right-hand side of the first order. Why do I have a first order equation here? Oh, right. This, excuse me, I went to the wrong code. I want just second order here. Excuse me. I referenced the wrong code. There we go. Copy. And let's see, let's paste everything below here. Paste. I'm glad I checked that before I assigned it. All right, that looks better. That looks more complicated. Okay, so we have our graph. We have our function graph. Yeah, that's fine. Set initial conditions, set initial step size, set minimal step size. Okay, that's fine. Set relative change tolerance. So this is all method related. So they might need to tweak these. Let's see here. This is the part where I need to make a little bit of a change because in the Euler-Cromer method, I'm explicitly referencing force and momentum. Here I'm just referencing the second differential equation, the second order differential equation, right? So this needs to be, let's make this, all right, I already have fun defined. Oh, we don't have fun defined over here. That's right. Equal to force divided by mass. Fun. This should be the force on the object divided by the object's mass. There we go. And I'll let them figure out how to work that in. Let's get rid of the extra little piece there. Let's see here. I guess I need to put in the things. Well, no, I didn't worry about putting in the things mass here. Okay, this is where I have to make my codes make sense together. So let's see. Let's divide that. Why don't we just do this? Let's make it a function of xv and mass. Okay. And because I need to be able to, right, because I need to be able to have derivs here and then have this be xv. Oh wait, so instead of being xv divided by mass, I want that to be a comma, excuse me. So let's actually put in another argument here for the mass, comma mass, comma mass, comma mass. And I was taught to make arguments align when possible. There we go. Future Brian here. I realized that another major difference is that since I was working with momentum, the first differential equation we have to solve is dp dt equals force. And then instead of having the velocity stored here, I needed to have the momentum. And so I need to get rid of this divide by mass. So this should just be the force on the object. And then this part that I return as the velocity should be the momentum here divided by mass. So I've replaced all of my velocities with momenta, and as you can see, the code is still working just fine. So just ignore that mistake for the rest of the video. I promise it's fixed on the file you can download below. Okay, and here, let's just make a note here. This vector contains the position x and the velocity v. And I suppose what that means is that back over here in Euler-Cromer, I have to make sure that the force is one-dimensional, that it's only going to act in the x direction, because my Runge-Kutta is only designed to act in one dimension, which should be fine. Back here in these instructions, I just have them describe the motion. So if I just give them the, all I have to do is make sure to give them the initial conditions. Let me make a little note to myself. For research methods, make sure ECM and RK4 force and initial conditions are only one dimensional. And actually that shouldn't be a problem, because when I make the, when I make the graph here, I do have a Y graph and a Z graph. Okay, I'm glad I pondered this. Oh, that's right, they had to change a few of these. Okay, right. This is just for their new problem. Okay, so not the spring force. Make sure force initial conditions for the new problem, not spring, or I'll say after spring force, because that I'll give them in the assignment instructions, not in the project template. Okay, I'm fine with that. Okay, I'll just remember that note to myself. Okay, students, if you are watching this and I gave you something two-dimensional or three-dimensional in the Runge-Kutta project, please point at this point in the video and say, I wasn't supposed to do that. This is past Brian. Okay, so the rest should be fine. I'll have an animation and a graph. I'm wondering if I need to include these print statements. I suppose I do. I suppose I should leave those in because the students should be aware of when it's changing step size. Okay, and then I have them compare the results of the ECM and RK4. Actually, need to finish writing the instructions up here, don't I? The following code cell contains the implementation of the Runge-Kutta method presented in this video to solve for the motion of a ball under the influence of a spring force. Change the initial conditions, force, maximum time, etc. in this code to match those from your Euler-Cromer method code above. The only significant difference between these codes should be the method employed. And then we'll say Euler-Cromer versus Runge-Kutta employed. I think that's, I think that's sufficiently vague that they have to reason through what is the method and what is the physics. Okay, so where do I want to have the instructions for comparing the two? I think I should have that after this. Okay. So that means I'm going to need another cell. So there's a lot of setup here. There's more. There's a more complicated setup here than I thought, which is okay. Here we'll have the instructions. So replace the text in this markdown cell. How did I phrase that over here? Okay, replace these instructions with a discussion of the following questions. There we go. Replace the instructions in this markdown cell with a discussion of the following questions. Okay, so what do I want them to do here? The learning objective is compare the steps of the Euler-Cromer method with those of the Runge-Kutta method. Okay. Replace the instructions in this markdown cell with a discussion of the following questions. Okay, let's see. How are these, what steps, generically speaking, do the Euler-Cromer method and the Runge-Kutta method have in common, generically speaking, in a general sense? Maybe I should preface it with that. In a general sense, because I want them to speak, I want them to speak in terms of the overall flow of the code. Like, what actions do they do in common, even if they look different? What steps do the Euler-Cromer method have in common, even if those steps are implemented differently? And then I want to number these. 1. It turns blue to tell me that I'm doing something different, that I'm numbering a list. Actually, here's how I want to phrase this. At a general level, and then I want to say, oops, at a specific level, what steps do the Euler-Cromer, what steps does the Runge-Kutta method perform differently than the Euler-Cromer method? And then I would say, how are these steps different? All right, maybe I need to use the word step differently because maybe I need to distinguish what I'm talking about, and also I need to distinguish it from step size, which is a big deal up in this Runge-Kutta code. What processes, even if those processes are implemented differently, what actions does the perform differently? How are these actions different? There we go. I think I like that better. Process is overall, action is specific line by line. So so process in my mind is at an overall structural level, and then action is at a line by line level. At a general structural level, at a specific line by line level. There we go. I think I'm queuing them into what I want there. Okay, learning objective 2. Compare the results of the ECM and RK4. Should I just introduce those abbreviations so I don't have to keep writing them? No, I think that's fine. But I will just copy and paste here. Copy, compare the results of the Euler-Cromer method and the Runge-Kutta method. All right. Run both codes above. And examine their results. Animation and graphs. Actually, the animation I don't care that much about, particularly the graphs. I suppose I need to get these on the same graph, don't I? Well, maybe not. Maybe not. We'll see. We'll see whether I need them on the same graph. Run both codes above and examine their results, particularly their graphs. Replace the instructions in this markdown cell. And then after this project, I think I'm going to stop saying replace instructions markdown cell and just say answer these questions, and hopefully they'll know to replace them. With a discussion of the following questions. All right, number 1. Okay, so let's think about this. At what points in the graphs do the results of these methods differ? 2. Why? Okay, let's think about this, Brian. Because I want to bring in the adaptive step size, right? Yeah. I shouldn't say at what point. In what regions in the graphs, yes. Do any of these differences correspond to the Runge-Kutta method changing its step size? And then 3, why are the results in these? Number 3, what causes the results in these differences? Hint, it's not just the changing step size, because there's the changing step size, and then there's the other thing that the Runge-Kutta method does differently. Number 4, which method do you find produces more accurate results? Why? Give you a hint. It should have something to do with the answer to question 3. Okay, cool. So we've got them comparing the methods, and then immediately after that, they're comparing the results. And I like that because they should have to, because because the discussion of the differences in the method leads directly into the comparison of the results. Now the question is, do I want to have, pedagogically speaking, do I want to have learning objective 1 all the way up here? Because they're not actually making the comparison yet. How did I frame it up here? I had learning objective 1, and then I had a lot of this. And then, did I have them do anything with response to that? Let's see here. Jupyter records information in cells. Then add your name to the title. Then remove the rest of the text in the cell, including the instructions, and replace with a 4-sentence description of what you hope to learn. Okay, right. So I had... Okay, so I had that at the beginning. So how about this? In that vein, let's move this learning objective down to here. So that I have learning objective 1, but I'm going to change this to learning objective 2 because they're doing activity up here above that I want to be a learning objective. Learning objective 1, setting, do I have it as ing or a verb? No, I have them as action verb. No, not action verbs, as commands. Set imperative, excuse me, that's the appropriate term. Set up the Euler-Cromer method and the Runge-Kutta method. Do I need to have them write anything? I don't think I need to have them write anything for this, now that I think about it, because I have here the, they are doing something. They are copying and pasting this here, and then they have the Runge-Kutta method here. So I think that's actually okay. But then this doesn't turn into much of a report, I guess. You know what? I'll worry about that in future reports. I think I might be extending that a bit too much. Having them write a full-fledged report is not yet a learning objective at this level, at this point in the semester. This is only their second project of like 5. Okay, so run both codes above and examine their differences. Replace the instructions as marked down so with a discussion of the following questions. Okay, I like that. Compare the results. Oh, excuse me, only this needs to be learning objective 3 now. Learning objective 3, control enter, control enter. I don't want to control enter that. I'm not interested in running it. Well, actually, I suppose I do need to run it, make sure it works, don't I? Okay, let's hit control enter to run. I think... Oh, excuse me. This needs to be else if. There we go. Did I have that mistake in here? Oh yeah, I did. Excuse me, folks. I need to make a correction to a code from another video. There we go. I guess that must be an okay construction in GlowScript. Okay, let's try that. Control Enter. Expected an indentation block. Line 74. Oh, right. I need to indent that if it's going to be under that. Tab. Oh, so I need to do the same thing over here. Haha. Tab. There we go. All right. Control Enter. Line 78. Invalid syntax. Oh, right. That'll need to be indented as well. Excuse me. So then this guy needs to be indented as well. Control Enter. Let's see here, mass and, oh, right, I actually have to give it a mass if I'm going to use that. Let's see here, initial conditions, we'll go with a mass equals 1. Oh, right, I have a bunch of other arguments over here I have to worry about. All right, then, comma, mass, copy, paste. And we'll make those align just to make it pretty. Okay, it's running my step sizes. It's not giving me my animation or a graph. Although, did this have an animation? I think this just had a graph. That's okay. should be giving me a graph. Give me my graph. Let's try restart the kernel. And then we'll run this cell. Okay, there we go. I just had to restart the kernel. Okay, good. So that's working. We can stop that there. All right. I'm a little concerned that I've had unsaved changes for a while. Save and checkpoint. There we go. Oh, now it's telling me it's auto-saved. Okay. All right. So all of that is working. That's fine. Compare these. Okay, I've written that one. I've written this part. Now I need to write this next part. Adjust the initial conditions. Okay, let's see. That should be the instruction. So let's here have produce new physical behavior. Okay. Copy and paste the Runge-Kutta code above into the code cell below. Let's see. Copy and paste your edited Runge-Kutta code above into the code cell below. Adjust the initial conditions in this next code until you find one set of initial conditions that produces a bound state and one set of initial conditions that produces a scattering state. Recall from class that a bound state occurs when the particle, let's say object, when the object, no, sorry, I'm getting ahead of myself. Recall from class that a bound state occurs when the object oscillates back and forth between two extreme values of position called turning points, and that a scattering state occurs when the object flies away and never returns. Let's see, let's do a little bit of formatting on this, that a bound state occurs and that a scattering state, and then we'll have here the same things in, I think this is going to be italics. Enter. Oh no, those are italics. Let's see if is there a way to get bold? I think double asterisk. Oh yeah, double asterisk does bold. Okay, let's do bold for vocabulary words. I remember being in college and thinking, none of these books has a glossary at the back. So all I wanted in college was for my, well, I wanted a lot of things in college, but one of the things I wanted in college was just for my textbooks to have glossaries in the back. All right, so we have paste your edited Runge-Kutta code here. Have fun with the initial conditions. All right, so let's review this. Produce new physical behavior. Copy and paste your edited Runge-Kutta code above into the code cell below. Adjust the initial conditions in this next code until you find one set of initial conditions that produces a bound state and one set of initial conditions that produces a scattering state. Recall from class that a bound state occurs when the object oscillates back and forth between two extreme values of position called turning points, and that a scattering state occurs when the object flies away and never returns. Replace the instructions in this markdown cell with a record of the initial conditions that you found, labeled by the type of state they produce. So we're trying to do a little bit of training in lab notebooks here. All right, then learning objective 5, finally. Discuss the differences between the states and the conditions that produce them. Okay. Discuss the resulting different motion. Discuss the different motion. Discuss the different results. There we go. All right. Replace the instructions in this markdown cell. Excuse me, that should be this markdown cell with a discussion of the following questions. Number 1. All right, let's discuss each of the states to begin with. What were the turning points of the bound state that you found? Number 2, at what point were you fairly certain, at what point in the results were you fairly certain that you had found a scattering state? Maybe we can make that a little bit better. At what point in the results for your scattering state were you fairly certain that the object would not return? 3. What is different about the initial conditions between the two states? Obviously, the numerical values that you entered are different. But what physical differences do they introduce in the problem that causes the motion to behave so qualitatively differently? I hate adverb. That causes such qualitative difference, causes this qualitative difference in the motion. In other words, I don't want them to say, oh, well, 1 was 3 and 1 was 5. Okay, that doesn't tell us anything. They are qualitatively different behavior. They're drastically different behavior. All right, learning objective 5, discuss the different results. Replace the instructions in this markdown cell with a discussion of the following questions. Number 1, what were the turning points of the bound state that you found? Number 2, at what point in the results for your scattering state were you fairly certain that the object would not return? Number 3, what is different about the initial conditions between the two states? Obviously, the numerical values that you entered are different, but what physical differences do they introduce in the problem that cause this qualitative difference in the motion? And I think I'll put a hint here because I want them... we might have a discussion of energy in class, but I want them to reference energy here. Hint. Think about, all right, how do I cue them into energy? Okay, think about an important quantity besides force that you learned about in your first physics course. Besides force that you learned about in your first physics course. Okay, I'm happy with that. Okay, so we've got set up the Euler-Cromer Method and Runge-Kutta Method. In the cell immediately below, paste the, let's see, this should be code cell. In the code cell immediately below, paste the final version of the ECM they used at the end of the ECM project. The following code contains the implementation of the Runge-Kutta Method presented in YouTube video to solve for the motion of a ball under the influence of a spring force. Change the initial conditions for, I guess not necessarily a ball, of an object under the influence of a spring force. Change the initial conditions, force, maximum time, etc. in this code to match those from your Euler-Cromer Method code above. The only significant difference between these codes should be the method employed. Then we have the code that we verified as running correctly. Learning objective 2, compare the steps of the ECM with the RK4. Replace the instructions in this markdown cell with a discussion of the following questions. At a general structural level, what processes do the Euler-Cromer method and the Runge-Kutta method have in common? At a specific line-by-line level, what actions does the Runge-Kutta method perform differently than the Euler-Cromer method? How are these actions different? Run both codes above and examine their results, particularly their graphs. Replace the instructions in this markdown cell with a discussion of the following questions. Number 1, in what regions in the graphs do the results of these methods differ? Number 2, do any of these differences correspond to the Runge-Kutta method changing its step size? Number 3, what causes the results in these differences? Hint, it's not just the change in step size. Number 4, which method do you find produces more accurate results? Why? Let's see here. What causes how? Hint. The changing step size is just one of 2 answers. There we go. How about I just say, what are 2 differences that cause the What are 2 differences in the codes, in the methods, that cause these differing results? There we go. I like that. What are 2, except I haven't called them results up here. Oh, goodness. What are 2 differences in the methods that cause the differing results in the graphs? There we go. Hint! Then I have 2 there. No, so then I don't need the hint there. There we go. How so? Yeah, that's fine. Which method do you find produces more accurate results and why? All right, produce new physical behavior. Copy and paste your edited Runge-Kutta code above into the code cell below. Adjust the initial conditions in this next code until you find one set of initial conditions that produces a bound state and one set of initial conditions that produces a scattering state. If they don't remember what it is, their eyes should find the bolded terms down here. Recall from class that a bound state occurs when the object oscillates back and forth between 2 extreme values of position called turning points, and that a scattering state occurs when the object flies away and never returns. Replace the instructions in this markdown cell with a record of the initial conditions that you found labeled by the type of state they produce. Paste your edited Runge-Kutta code here. Have fun with the initial conditions. Learning Objective 5. Discuss the different results. Replace the instructions in this markdown cell with a discussion of the following questions. Number 1. What were the turning points of the bound state that you found? Number 2. At what point in the results of your scattering state were you fairly certain that the object would not return? What is different about the initial conditions between the 2 states? Obviously, the numerical values that you entered are different, but what physical differences do they introduce in the problem that causes qualitative difference in the motion? Hint, think about an important quantity besides force that you learned about in your first physics course. Okay, I am happy with that. Next time, we will move on to the numerical integration assignment. Very excited about that. Thank you so much for watching. I will see you next time. Bye-bye.